In this class, we will try to understand three terms which are already familiar to us, and they are heat capacity, specific heat capacity, and molar heat capacity. Heat capacity is defined as quantity of heat required to raise the temperature of a substance through unit temperature difference. That means either through 1 Kelvin or through 1 degree Celsius, because this difference in temperature in degree Celsius and Kelvin are same. Means you can write this heat capacity as delta Q by delta T, where delta Q is the heat energy required to raise the temperature through delta T. That means, suppose you have a substance and if you have to increase its temperature, say if you are giving say 10 joules of heat, and if its temperature is increased through say 2 degrees Celsius or 2 Kelvin, you can say that its heat capacity will be equal to 10 by 2, that means 5. And you can notice these points. When delta Q is equal to 0, that means in this, heat capacity will be equal to 0. And we know that for adiabatic processes, delta Q equal to 0. Therefore, for adiabatic processes, heat capacity equal to 0. And for isothermal processes, we know that the change in temperature during the processes are 0. That means delta T is equal to 0. So, this quantity is infinite. And unit for heat capacity is unit of heat is joule. Joule is the SI unit of heat. So it is joule per Kelvin. And actually, you are considering this joule as unit for energy. And in SI system, any type of energy are mentioning the same unit. And in olden days, we were used calorie as unit for heat, and it is in CGS system. And in SI, it is joule. So heat capacity is joule per Kelvin. And this heat capacity depends on mass. That we can understand. Suppose you want to raise the temperature of say some 5 kilogram of water through 1 degree Celsius. You need some energy. And suppose it is say 10 kilogram. We need more energy. That means this heat capacity depends on mass. That means it is not a heat capacity depends on the mass, and it is not the property of a substance. For that, we have to define this quantity for unit mass, and that quantity you are calling as the specific heat capacity. It is the quantity of heat required to raise the temperature of 1 kilogram of a substance through unit temperature difference. That means 1 kilo Kelvin or 1 degree Celsius. So, by dividing your heat capacity with the mass, you can get the specific heat capacity. Specific heat capacity 1 by m delta Q by delta T, where delta Q is the heat energy required to raise the temperature of mass m through delta T. And its unit is joule per kilogram Kelvin. And we are just mentioning a value. for doing problems, we need normally this quantity. Actually, the specific heat capacity of water you are considering as 1 calorie per gram. And in joule, in CGS, this is a CGS value, and in SI, it will be equal to 4200 joule per kilogram Kelvin. We can just note this conversion. This is also known to you. 1 calorie is equal to 4.2 joules. This 4.2 joule, sometime you are taking as 4.18. So, roughly we can consider it as 1 calorie equal to 4.2 joule. And 1 kilogram is 10 raised to minus 3 kilogram. So, this 1 calorie per gram you can write as 4.2 joule by 10 raised to minus 3 kilogram, which will be, this will be going upside. So, it will be 4.2 10 raised to 3. So, it will be 4200 joule per kilogram. Okay. And this quantity is also something which can be easily remembered. The specific heat capacity of ice is half that of water. So, it will be 0.5 calorie per gram or 2100 joule per kilogram, not per Kelvin, joule per kilogram Kelvin. And we have one more term known as molar heat capacity. It is the quantity of heat required to raise the temperature of 1 mole of a substance through unit temperature difference. When you are just mentioning about a body or system without considering its mass, etc., just for a particular substance through 1 degree Celsius or 1 Kelvin, it is the heat capacity. And when it is for 1 kilogram, you are calling it as specific heat capacity. And when it is for 1 mole, you are calling it as molar heat capacity. And now, just note this. You can have this concept. Temperature difference in degree Celsius and in Kelvin are same. That means in that expression, we are considering delta T. That means change in temperature, which can be either in degree Celsius or in Kelvin. There is no difference that we can note here. Temperature of ice you can take as, or you note it as 0 degree Celsius, or in Kelvin it is 273 Kelvin. And temperature of boiling water is 100 degrees Celsius, or it is 373 Kelvin. So, difference between the temperatures equal to 100 degrees Celsius in degree Celsius scale. And it is 373 minus 273, which is same as 100 Kelvin in Kelvin scale. That means that difference is same, 100. And for gases, there are 2 specific heats, which is also known to us. That means that you can consider it as at a constant volume and at a constant pressure. And they are normally represented as, this is the specific heat capacity at a constant volume, and this is specific heat capacity at a constant pressure as Cp, Cv and Cv. And the ratio of specific heats is represented as gamma Cp by Cv. In representing an adiabatic process, we have written it as PV raised to gamma, where that gamma stands for Cp by Cv. And also this difference, Cp minus Cv, is represented as R. For 1 mole, it is Cp minus Cv is equal to R. And this is your Mayer's relation. This R is the universal gas constant. And now, principle of method of mixtures, and this is much useful for solving problems. The principle of method of mixtures states that under adiabatic conditions, heat gained by the cold body is equal to the heat lost by hot body. So when you are mixing a hot body and a cold body, you are considering that heat transfer is taking place at adiabatic conditions. So if one is at a higher temperature, other at a low, heat will be flowing from the body at a higher temperature to the body at a lower temperature, and then that flow will continue until both of them are at the same temperature. So when heat is flowing from the body at a higher temperature, its temperature will be decreasing. And when heat is flowing into the body at the lower temperature, due to that heat flow towards it, its temperature will increase. So the temperature of hot body will decrease, temperature of cold body will increase, and after some time they will reach the same value. That means the intermediate temperature or the resulting temperature. If you consider masses of M1 having specific heat capacity C1 at a temperature T1 is kept in contact with another body of mass M2 having specific heat capacity C2 at a temperature T2, then by the principle of method of mixtures, you can write as, we are also assuming that temperature T1 is greater than T2. So if T is the intermediate temperature, you can write as M1C1 into T1 minus T. This you are getting from this equation. You have C is equal to 1 by M delta Q by delta T. So delta Q will be equal to MC delta T. So mass into specific heat into this delta T is the difference in temperature that you are writing as T1 minus T. And for the cold body, which is M2C2 into T minus T2. And by solving this, you can have the, and suppose if you know 1, 2, 3, 4, 5, 6, 7 quantities are here. And from this, if 6 are known, you can calculate the remaining. So this is normally used in solving problems. And that all in this unit. So from this discussion, our first unit is over, and thank you.